Okay guys, so I-beam. This is aluminum I-beam. The Fig and Denny Pate, Fig Engineering, Linda Fig, Denny Pate all describe their structure as an I-beam. I-beam, solid webbing, top flange, lower flange, webbing, but cutouts, anchored with nodal areas in the lower on the top deck with steel, post-tension bars, blisters at the top, blister bars at the top connecting these nodal areas. Down here I left this open. This would be number 1 and 2. Down here would be our failed section. Now I'm working a couple angles on this for you to help you visualize it. Right now this would be the diaphragm, if you will. That's the part that's hanging off. This concrete, this block would be the diaphragm. Same thing down here. Remember, there's an expansion joint here and a column. We don't have anything going on with this column. Nothing to cry about. If I would suggest, put this aside for a second. If I would just put a load on this column, on this I-beam, the load would pretty much transfer 1-to-1 straight through down to there. That's in compression. Now there's some theoretical flange in this, even with this weight, some loads inside the flange, tapering off, coming back to the web and going down through the web. Maybe a little bit of, if you could see it, a little bit of, if you could finite it so accurately, you might see a little bit of highlight here and tapering off this way and that way, and then into the web, transferring maybe down here into like a 45 into the steel, into the base below it. Well, that's just to help you visualize it. But you can see I can load this, since it's on a flat surface, continuously everywhere, no deflection. It would just be all under compression. Again, Linda Fig, Denny Pate, the system's all under compression. There is no tension to it. The moment you add tension, you no longer have their system. It's no longer the system, their intended system. It becomes a truss system, which I argue can exist. Compression, all compressor system and a truss system can't exist together. Cannot exist together because the truss wants to do the compression, tension, transfer the loads downwards, depending on where the loads are. Now loads are pretty much calculated here at each connection, not between. It's just transferring the loads. If you put a load here, it's just transferring a load out to here. But you can imagine if I could put a heavy enough load in here, I would create this uplift between the two of them. But this would be strong enough to deviate, to stop that. If this was a car up top, a lower deck, upper deck, if you will, this bridge decking would transfer the loads out to the nodal areas and down again. This being that weird configuration drives everybody crazy. You can obviously see that you can't have this acting as a truss system. It just doesn't work. It's the configuration of the columns wouldn't act like a truss system. They have no choice but to try to act like one, but they because the connections would make them want to do that, but it would be quite an irregular pattern of transferring the loads down to one end to the other. So I have this on the diaphragm there, but I'd have that hanging off the deck. Initially in the staging area, cracks developed right here. Now I have this off for clarity, but I'll put some stuff on for you guys. It might be a little, might need to visualize it. That's where that crack is, remember? This is where they state that number 11 pushed off 12. So right here, it's not connected. I don't have it connected, so you can see what happens. That I can lift 12 up from this point here, creating an action. They put shims underneath for that structure. So once they put shims under there, look what happens once they shimmed it. They created more of a problem. You see, as I put a load, that's the dead load of the structure now. By shimming this outside 12, they created more of an uplift issue. But what would hold this together to this, back to the diaphragm area, is that number 11 has 2 bars in it. One's in the base of 11, which is tacked here, indicating that. I'm going to run a piece of rebar or all thread or something like that, a screw probably, a bolt with this one. from here to here to show you what happens when I create that clamp force. It's going to pull it back in and hold it in. You can imagine if I were to loosen the bolt, it would come apart. And that's what the crack like hell presented, the loosened bolt. But I want to show you that the dead load, I'm going to add this 45-pound weight, well, 5 pounds. Just a 5-pound weight in this scale thing. And I'm using the center loading it. And you can see what's happening there. This is kicking out, creating that outward action. Number 11 does not have to push outwards. I'm sorry, it's very cold here, guys. It's like 20 degrees. I'm starting to shiver and voice shudder. This is where cracks are presented in number 11. So I have it not non-cracks in it, but I'm showing that it wasn't pushing anyway. So I'm actually giving it the extra support of number 11. And I'm going to add another weight to it. And you can just see what happens there. Now what would keep that together, again, is the bar, the rod that's in here, keeping that from kicking out. So that you can imagine the forces are in the back of here and in the back of 12. And then we get this cracking. But you see the uplift? So I just wanted to show you that. There you go. Down here we don't have an issue going on, so I'm not really concerned about that this time. I'm going to load this video up because I'm about frozen, and we'll talk about this some more.